Okay, welcome back. In today's class, we'll continue from where we left off last time. Last time, we had an informal discussion on what was included, and now we'll just look at it in a more formal sense in terms of the terms involved. Some of these, in fact, we discussed just in the context of whatever we were discussing earlier, but we'll try to do it a little more formally today. Okay. Also, as one of you was asking, today at 4 p.m., some of you might have seen the email. There's one of our NM cadets who is not defending, but presenting his PhD colloquium. So those of you who are interested in that particular field are welcome to attend that immediately after the class. It's on the same floor in the STC seminar hall. That's about low velocity impact. It also involves compression. So these are essentially for metallic foams, in particular aluminum foams. As you know, there are a lot of sandwich constructions which are used in aerospace engineering because the bending stiffnesses are very high for that. Very similar to an I-beam, for example, in civil engineering. And when you're using that kind of construction, you typically need a high shear performing core. And that core is typically aluminum honeycomb, which is used, or foams which are non-metallic in nature. But this is a situation where we are trying to look at, especially for impact applications, low velocity in this particular case. What would happen if you can use aluminum foam instead of non-metallic foams, and you'd see the advantages of that. So that's what the student will be presenting. So those of you who are interested in any of these aspects are most welcome to attend that. Okay. So continuing with A201, we have a set of formal syllabus. I told you the course is divided into 1/3 each, but right now let's look at it purely from atmospheric flight and space flight point of view, in which case we can think of it as two parts. So where the third part, of course, comes is from this part onwards. So in other words, just the aircraft performance alone is going to take the first 1/3, because as I said, this is essentially designed for those with a non-AE BTech background or BS background, which means that a little bit of the aerodynamics and propulsion will be reviewed here. And we'll also look at where this is essentially operating in, because even though this will, the physics and the math involved will be generally applicable for all other atmospheres. I talked about Venus and Jupiter atmosphere, for example, or even Mars atmosphere in the last class. But now our focus will be on the Earth's atmosphere for flights which are happening above the Earth's surface, typically about 10 to 12 kilometers for most of the commercial aircraft, and also many military aircraft, even if they operate at higher altitudes or lower altitudes, may sometimes get into that particular altitude. So it's of significance to all kinds of aircraft. So that's as far as the atmosphere is concerned. So what is it about the atmosphere that is going to be important as far as understanding flight mechanics and in particular performance is concerned? Any takes? Why is studying the atmosphere so very important before we get into understanding aircraft performance? Okay, very good. Yeah, so how does knowing the density help? Uh-huh.
So that will directly be dependent as a function of the atmospheric, the air density.
Very good. Okay.
Altitudes, which
Yeah.
vary and decrease as you go up in altitude.
Okay, very good. Yeah, so density is a very important characteristic of the atmosphere, and understanding how it, not only what its value is at the surface or at that particular altitude where we are cruising, but the entire distance in between, how it varies is a very important thing. Anything else? Temperature, yeah. Why is temperature important?
Total energy of air inlet to the propulsion.
Okay, okay.
So it also decides
Very good, yeah.
the sound at different altitudes.
Exactly, yeah. So essentially, as she said, the sound is square root of gamma RT, where gamma and R are constants for air, 1.4 and 287 in SI units, and therefore the temperature, square root of the temperature will determine the speed and therefore the Mach number. And what you're talking about, the inlet temperature is also very, very critical in terms of the engine performance and the thrust that you get. Even the specific fuel consumption, all of these can be dictated by the temperature profile and what the particular temperature is where the aircraft is flying. So density and temperature, what else? Pressure, yeah. Why is pressure important?
So, like there, due to pressure difference, the turbulence might be there also.
Okay.
And also, like our engine performance will also change with respect to the pressure condition it is operating.
Okay.
Sir,
Yeah.
lift is primarily because of the thermodynamic pressure.
Yeah.
And sir, so the difference across the lifting surfaces create that. So
pressure difference of nozzle and atmosphere is also included in the thrust equation.
Mm-hmm.
So atmosphere pressure is to be low.
Yeah, yeah. So many different reasons. So some of these you mentioned are secondary, but some of these what you mentioned are primary reasons. So it's very, very critical to understand the pressure distribution also, which is why in the beginning I was talking to you about what is the pressure at top of Mount Everest. Just to get you an idea, it's dropping to 1/3 of the surface pressure, and at about 10-12 kilometers it's even lesser, 1/3.5 approximately at typical cruise altitudes for most commercial aircraft, because slightly higher than that. And also another thing that I mentioned in passing in the beginning of last class is that it's also important for us to talk the same language. Okay, so not only teacher and student, but also more importantly, as I said, in terms of the designers and who is going to implement the design, execute the design. Also between the ATC, which is the air traffic controller, and the pilots who are flying the aircraft. So because there are so many different things in terms of definitions for pressure, temperature, and the density, we will see that also some varied examples also. So it's important that which particular pressure or which particular density or which particular temperature that you're talking about. And it's not just the units, but also in terms of the actual definition itself, which is what is very important. Otherwise, you might be talking about two different things, and the communication will not be effective enough, and that could be sometimes disastrous. So that's why studying the atmosphere is very important. And then, as I said, we'd also takeaways in terms of how we would like to design an aircraft, let's say for Mars landing or Venus landing, where the densities are much, much lesser or much, much higher respectively. And therefore, you need to understand, of course, the composition is also important. Apart from pressure, density, and temperature, the chemical composition of the atmosphere is also important. Here, as you know, it's predominantly nitrogen and oxygen, which make up almost 99%. And next comes argon, and then all the other gases. So understanding that helps, especially when you're looking at air breathing propulsion that you're talking about, where oxygen is so important for the combustion process to take place for the kind of fossil fuels that we typically use. So that's where the study of the atmosphere will come from. I may not go exactly in this particular order. This is the order in which it is listed in your scheme of instructions. So I might sometimes jumble up depending upon the flow of thought. I might jumble up the order, but essentially, and also this is more like a wish list. I hope we will cover all of these things. Even if we don't cover it in the extent to which I would desire it, I would at least touch upon all of these things. So, which is what is the plan for this? In a lot of places, instead of calling this kind of a course as flight mechanics, they call it as aircraft performance itself. So that's the name of the course itself. In fact, there is a separate course for aircraft performance, separate course for stability, again for static stability and dynamic stability. And this whole thing is comes under orbital mechanics or space flight, right? So we are trying to, and each one of them is typically like a 3-credit course, especially in undergraduate aerospace programs, which many of you have been part of. You would see that that's how it is structured. So here it's trying to put all of them together in a 4-credit course and trying to do reasonable justice for all of them. Just at least you're familiar with the terminology. As I said, any new subject, as long as you know the terminology, it's half the work done. because then it's the same physics and math that you're essentially playing around with. So that's as far as the atmosphere is concerned. We will go into the details as we go forward. The next thing is an introduction to the aerodynamics and propulsion. Just to avoid clutter in my slides, I might be always using short forms for all of these. Just get used to that. But if you don't, these are not such great things to remember anyway. So if you don't understand something that I've written, just ask me and I'll tell you what I mean by that. Okay, it's for my own understanding in terms of a prompt, because I expect more of the knowledge transfer to take place from what I'm speaking rather than what you see on the slides. This is for me not to lose track, and also just to come back and to see if I've done everything that I wanted to do, right? So propulsion. So aerodynamics, the reason why it is important obviously is some of the forces are going to be determined by the aerodynamics. So a very basic understanding of the fluid dynamics that you did in the previous semester, and translating that for airflow is what is essential. So some of you are asking me over email that is it okay if you have not done a fluid dynamics course, especially those who are not MTech students, first year MTech students. So then as I said to you already, absolutely no issues, because whatever aerodynamics is required to understand the aircraft performance, those aspects I will try to cover in aerodynamics. And if I happen to miss out something, whenever that particular aspect in the performance comes up, I will try to touch upon that. So absolutely no worries. As I said, there's no official prerequisite to this particular course. So even though having done all those 4 courses in the previous semester, plus the 2 math and experiments will help you better understand this, it's not essential or it's not necessary, right? So that's as far as the aerodynamics is concerned, because 2 of the important forces, lift and drag in particular, are going to be coming out of that. A lot of the moments are going to be coming out of that, be it the pitching moment, the rolling moment, or yawing moment. Many of those will be dictated by the aerodynamics once again. And as far as the propulsion is concerned, the other important force that we need to generate, unless you're designing a glider, for example, in which case you don't need that, is thrust. And in order to generate that thrust, you need to understand some basic aspects of propulsion. Most aircraft today use jet engines, which is essentially a translation of the on-surface gas turbine technologies to the flight, and essentially trying to understand certain aspects of that, be it turbofan, turbojet, ramjet, scramjet, or whatever. And of course, some of the low-speed regional aircraft for short hauls typically continue to use turboprop, and even smaller ones at smaller speeds continue to use piston props using the internal combustion engine. These are typically like home-built aircraft or for acrobatics and things like that. So some basic aspects of those things will be covered in that propulsion. We'll also require propulsion for this particular thing, because launch vehicles, whether in missiles or for launching satellites, you will need rockets, and therefore the rocket engine propulsion, which is slightly different in understanding. Very interestingly, if you look at the literature, those who work on rocket are called scientists. Typically, you say, is this rocket science? To say something is very difficult. On the other hand, anything else related to aerospace is engineers. So engineers are technologists, but that's more of a colloquial usage. In essence, both of them require as much science and as well as engineering. So there's no difference as such, right? Next, we go on to the primary core of this particular course. The rest are all just to get to understand this better. So that's your aircraft performance. And aircraft, by which we mean predominantly a fixed wing, the helicopter as well as the flapping wing mechanisms are far more complicated, both in terms of the mechanism itself and also in terms of the aerodynamics that is involved over there, the couplings, etc. So we will not dare to venture that, but if you're interested, some of you, on certain aspects of that, you're most welcome to have after class discussions. Okay, so that's as far as aircraft performance is concerned. And in the previous class, we drew an analogy between you going to purchase a 2 or 4 wheeler and what kind of performance features you're going to look at, and therefore what are the similarities in terms of an aircraft. Yes, you have the same set of things, but in a little more nuanced way. For example, when we talked about speeds, we talked about not only a maximum speed, but also a minimum speed, which is essentially associated with stall, etc. So we will try to touch upon those things, and also in particular the VN diagram, etc. And in today's class, or hopefully at least the next class, this Wednesday we will not have a class as Makar Sankranti Pongal. In fact, today the International Kite Festival was inaugurated in Gujarat. The German Chancellor was also there as a guest. So very, very interesting in terms of kite aerodynamics. One of my co-students, I would say, who worked, I think about a year or two after me, a junior, who worked with the same PhD advisor, predominantly worked on kite aerodynamics, and we were all jealous of him, the kind of interesting things that they could do and actually play around with it. And as soon as you try to understand some science or the engineering aspect of it, you can actually do it and test it for yourself. You don't need to depend on certain technicians at the lab, etc. Right? So, and a lot of understanding. In last class, we talked about paper airplanes. Okay, that also gives a lot of understanding in terms of some of these aerodynamics. It may not look like the actual mechanisms that are involved in the kind of aircraft that is put up on the table over here, but you know that you see some of the basic aspects. Like, for example, if you're bending the rear end of that paper aircraft, essentially what you're trying to do is to readjust the elevator setting. In a very, very crude sense, but that's exactly what you're doing, so that you can balance it better or increase or decrease the stability, as the case might be, depending upon the original design. So all that is what we will be looking at in aircraft performance. In fact, we will start off with exactly the opposite line, like what we did in the previous class. We were trying to look at similarities with surface vehicles as far as flight vehicles are concerned. Today, we will try to see what are the differences, and which is why we are in this particular course. We're trying to understand how we can get that extra thing which surface vehicles are not able to do unless they are flying cars. So then, so that covers pretty much the first 1/3, and then we will get into the stability aspects. So next is stability, which gets divided into 2 parts: static and dynamic stability. Anybody recognizes, either from their own studies or their previous courses in undergrad, what is the difference between these 2 stabilities, static and dynamic?
Static is the initial tendency of any body once it is disturbed.
Right.
Dynamic stability deals with the time, like after some time, what is the position or the orientation of the body.
Absolutely, yeah. So essentially, you're looking at, as he very rightly used the right kind of words, the tendencies that are there. So the typical example that is used, which you might be very familiar with, is essentially to describe the 3 different situations: so a ball in a bowl, or on a flat plate, or on top of the inverted bowl. And you see that these are all trying to look at the static stability. Okay, so we say statically stable, statically neutrally stable, and statically unstable. Okay, so essentially what is happening is, if you disturb this, then it tends to come back. So the initial tendency, so if I take it to some location over here, then the initial tendency is to come back. And typically in real life, these have friction in between the two, and essentially the amplitude of that swing, it will overshoot, and then it will essentially come back to the original equilibrium position. right? So we say it's an equilibrium position originally because the forces are all balanced. It's a static equilibrium in particular, right? Now that static equilibrium state is stable in the sense that any disturbance that you're having, small disturbances, are essentially going to try to bring it back, because you can actually push this to the top of the rim over here and then say the initial tendency is for it to fall out. We're essentially talking of small disturbances over there, small in a sense of relating it to something else, let's say the diameter of the ball or whatever, right? So in that sense, and as you rightly pointed out, the dynamic stability is, does it eventually come back? So in this case, as I said, because there is friction, it will eventually, the amplitudes of that overshoot will come down and it will essentially come back. So essentially it's not only statically stable but also dynamically stable. But there could be, can you think of an example where it is statically stable but not dynamically stable? Very good, yeah. So yeah, bicycle, yeah, bicycle, what aspect of the bicycle?
So when it is, it requires constant motion for it to be stable, and the telescopic moment makes it stable.
Very good, very good. Yeah, yeah. So these aspects, if some of you don't understand, it's okay. We will be covering those aspects also when we get there. So what he's talking about is the situation that you need a certain additional effort to keep it in that equilibrium state, or bring it back to that equilibrium state. Otherwise, this can grow. You can think of it where some kind of energy is being supplied to that, because of which the amplitudes start growing, in which case, even though the initial tendency was to come back to the equilibrium position, if the amplitudes are growing, then essentially it is dynamically unstable. So that's precisely what you'd be looking at over there, right? Yeah. So that's as far as static stability is concerned. We will be looking at static stability from the point of view of all these things that we described in the previous class. If you remember, we were talking about essentially the pitch, the yaw, and the roll, right? So these three are the attitudinal descriptions of the aircraft. Just like you need to specify the position of the aircraft by saying, even if you treat it as a rigid body, the center of gravity or the center of mass, where exactly it is at any given point in time, right? So as a function of time, you can follow the CG and see where exactly it is at some instant t naught, right? So similarly, for all t greater than t naught also, you can follow that depending upon how the aircraft actually flies. Now, for any given kind of position and orientation, if it is, first of all, we check whether it is in equilibrium like we did in that particular case. And once the state is in equilibrium, we can then study the static equilibrium of that. In other words, the roll stability, the yaw stability, and the pitch stability that you have, which are in turn related to the translational motions as well. Because in the last class, if you remember, I told you there is this plane of symmetry that we have the advantage of. So if we introduce x along the nose of the aircraft, y along the starboard, and z along the vertically downward direction, then you see that the xz plane that is there is essentially a plane of symmetry, right? Because of which we said that out of the 6 equations that you're going to get, 3 out of translation, 3 out of the rotations that are involved, rigid body like rotations. So you're going to have 3 of them decoupled, which is everything that is happening in the plane of that symmetry, which means that it's the forward motion which is happening in the x direction, and therefore it's in the xz plane. The vertical motion, which also could involve the climb that is there, and that is going to be the z motion, that is also a translation, which is also in the xz plane. And then the rotation about the y-axis, which is also in the xz plane, which is essentially your pitch that is going to be there, right? So all of these are coupled with each other, but they get decoupled from the other 3. What are the other 3? The other 3 are the rolling motion, the yawing motion, and the sideway drift that is there. Okay, so one translation and two rotations over there, right? So these three get coupled. How they get actually decoupled, we will see when we go into the math of that. Right now, you just understand from a physical argument that we made out of the plane of symmetry kind of an argument, right? So when we go to the so-called equations of motion, once again, it's an abbreviation that I'll be using very frequently. Just like I'll be talking of the degrees of freedom, okay? So depending upon the degrees of freedom that are involved, as we said, there are, for any rigid body, including this aircraft, if treated as a rigid body, there are 6 degrees of freedom, 3 translational and 3 rotational. So you can have a 3 degree of freedom system of equations. Even in the general case, because of the existence of the plane of symmetry, actually, even when you go to the 6th DOF problem, you can separate it out. But if you make some assumptions which are okay for a conceptual design or for an introductory class like this, but most of the time in real life it's not applicable, is when you try to bifurcate just the translation as a separate problem and the rotations as a separate problem. It really doesn't work very well, but that is one way of deducing the 3 degree of freedom system. So different literature, different books, what is referred to as 3 DOF could be different. So just take it with a pinch of salt, actually go into the details to check and see what exactly are they talking about over there. Whereas this, there's no doubt about it, because there are only 6 degrees of freedom for the rigid body, and only those will be accounted for in the 6 equations of motion you'll have in a corresponding sense. Whereas for this, you'll have only 3 equations of motion which you'll be dealing with, right? So those are certain things that we will try to take a look at, including what is crude, but pointing out what is the crudeness involved in it, so that we can avoid that when we are doing something more which needs a greater reliability. The next very important thing is translation is very, very easy to understand. You have your Newton's laws, which are force is equal to mass into acceleration. It's the second law. Or in a more refined sense, it's the rate of change of the translational momentum, which is equal to the net force or resultant force that is applied on the body. Okay, so when you have something like that, it's very directly easy to deal with that. Whereas an extended version of that, what is known as the Euler equations, not to confuse between the Euler equation or Euler model that is used in fluid dynamics. Here we are talking about rigid body rotations. And then you would have to deal with what are known as the attitude representation. Just like you have an XYZ for the CG, to exactly say where is that aircraft at a given point of time, you also need to know the attitude of that aircraft at the same time instant, which is in terms of what is the pitch angle, what is the yaw angle, what is the roll angle. So when you want to do that, you need to have a representation of the attitude, and that representation is not unique. There are many different ways in which the attitude could be represented. Each of it has its own advantages and disadvantages. So we'll try to look at some of those. Some of the more common ones you might have heard of are Euler parameters or Rodrigues parameters, etc. If you have not heard, don't bother, because we'll be introducing those as well. Just for those of you who know, trying to correlate with what I'm talking about over here. Because then that's what will enter the equations there in terms of understanding what changes with respect to time, how, and therefore how is it related to the other quantities which may also be changing with time or have a constant value, whatever it is. The correlation between them is what we get into the equations of motion, right? The next thing we'll be talking about is, as I said, the dynamic stability, as one of you already pointed out. Does it eventually come there? So that involves a little more deeper understanding. So typically, while we will cover this in reasonable detail, we may not be able to do as much justice, which is why I just mentioned its basics. We'll not go into deeply into understanding that. Even here, the equations of motion, we might come come up with the equations, but we may not look at solving it for certain problems, etc. Just an overall understanding of how the correlation takes place. Maybe we can take some very simplified situations where some of the terms vanish, and then we'll see how things are related to each other through those equations of motion. Next, the other aspect is a follow-up from what you did as part of navigation guidance and control course, trying to see how the flight control is going to be operating. We already talked about all those angles. We also talked about the pilot having either a control stick or a control wheel, which they need to move. It's quite intuitive for the pilot in terms of how it's moved, and also the rudder pedals, etc. But essentially how that is translated in reality, we discussed in the last class both mechanical ways of linking it as well as the fly-by-wire concept. So again, without going to the details of that, we'll try to touch upon that, what levels of forces and or moments are acceptable from a human point of view, and how typically a designer tries to address those things. And the final thing that we will talk about is essentially a transition to going from the first column of topics to the second column of topics over here. We're going to be looking at launch vehicle. So launch vehicles, LV term you're very familiar with, thanks to ISRO, talks about SLV, PSLV, GSLV, etc. Today, I think there was a PSLV firing, right? Okay. So then we're going to be talking about the flight basics there. Now, this is a unique animal which is going to be flying both in the atmosphere as well as in space, depending upon, of course, the mission that is involved. In which case we need to have an understanding, which is why I put it here. I might as well put it in that part. It would be equally applicable, right? So next, once that is done, we will get into the second part of it over here, which is the part 2, which is the space mechanics, where we will try to start off from an understanding historically how some of the great scientists of the 1600s and 1700s tried to understand the planetary motions, how Earth moves around the sun, how the other planets in our solar system move around the sun, or how the satellites, like in our case the moon, how it moves around the Earth, for that matter the many satellites that are there for Jupiter, Saturn, etc., how they move around those respective planets, etc. So there we are going to be talking about orbits. We're going to be essentially starting with the two-dimensional orbits, and then extending it to three-dimensional. If you're going to have some out-of-plane motion out of that, what is the kind of forces you need to generate, how you need to fire your rocket boosters or whatever you might have on board in order to enable that, right? So that's the, as far as the understanding of orbital mechanics is concerned. Then in order to change orbits, one of the reasons we discussed in the last class, for example, that it's cheaper to travel per kilometer by auto compared to, by Mangalyaan compared to an auto, is essentially because some of these maneuvers are thought well in ahead. You know the planetary motions, you know the motions of the rest of the bodies in the solar system. You're trying to take advantage of the gravitational forces of the bodies which are close by to the aircraft or the spacecraft at a given point of time, and then you're trying to ensure that a minimum amount of rocket fuel or propellant is burnt, and therefore essentially you're trying to kind of optimize the orbital transfers, in which case you need these maneuvers going forward from one orbit to another, right? Then the other thing is, of course, very critical is the docking. Like, for example, when the space shuttle goes to the International Space Station, or used to, because it's retired now. So essentially going and docking onto it in order for transfer of personnel and or resources, and then undocking to come back, right? So that's again a very, very specific maneuver. We might spend a few minutes talking about that. Coming to the interplanetary trajectories, going from, let's say, from one planet's atmosphere to another planet. Mostly we'll be talking about going from the Earth to any of the other planets or to the moon, etc. So there we need to see how it transfers. One, it's orbiting around the starting planet, and then eventually it's going to be orbiting about the desired planet or planetary body, and how it's going to transfer from one to the other. So that's essentially your interplanetary trajectories that you're going to be talking about. Then the planetary entry that is going to have. In other words, if you are sending something to Mangalyaan, it's entering the atmosphere of Mars, which means that it has to bear the kind of forces that are going to come from the gases that are going to be present, even though much less pressure and density compared to what is on Earth, but still the ability to deal with that, right? So the entry, whereas when you're coming into the Earth's atmosphere, re-entry, for example, the Gaganyaan eventually has to re-enter. The re-entry module design is very critical over there, because the temperatures which are reached will be very high because of aerodynamic heating. So we look at some very simple expressions or equations which will be able to estimate the kind of heat that is generated, the temperatures that are going to be experienced, and therefore are the materials capable of handling that. So that's the kind of things that we'll be looking at. Let's say, for example, carbon composites, etc., or ceramic tiles and etc., active cooling systems, or utilizing shocks in order to further reduce the temperature even before it reaches the vehicle, etc. So those are the aspects from planetary entry point of view that we will cover over there. The next thing that we'll be looking at is in terms of the descent and landing. As much as descent and landing and takeoff are very critical for fixed wing aircraft, it becomes even more critical when you are here, because a part of your vehicle is already lost in going up. Even while coming down, a lot is burnt off, and therefore what is remaining and how it's going to descend, where it's going to descend, how it's going to land without much of an impact or as minimal impact as is feasible, in order to safeguard whatever is inside for the next usage, as well as, of course, if it's human flight, even more critical aspects are involved. Next, we'll be talking about Lagrange points and halo orbits. Many of you, thanks to the Aditya mission, might be familiar with these terms. Anybody? Yeah, what do they mean?
There are 4 points.
Force are zero. Net force.
Yeah, net force is
Very good. Yeah. So why is it zero? What is happening?
due to gravitational field, their interaction between sun gravity fabric and earth gravity fabric will cancel out at that particular region.
Right. So most of the time when we'll be dealing with all of these, we'll be only considering one particular body, right? Because remember that Newton's law of gravitation gives the force as uppercase G, uppercase M, small m by r squared, right? So in other words, the r becomes a very critical. So this is the force due to gravitation is given by the universal gravitational constant, where r is the distance between these center of masses of these two bodies, the larger planetary body and the vehicle that you're dealing with, okay? So in most cases, it's only one body which is involved, because the r from all the other bodies is much larger, okay? And since r squared is involved there, yes, there are gravitational forces coming from everything else, but they are negligible compared to what we are dealing with from that body which is closest at a given point in the orbit or the interplanetary orbit, or whatever maneuvers you might be doing, right? Whereas these Lagrange points are such that at least two bodies are involved, and therefore there's a cancellation which is possible, because these forces can be in opposite directions and from each of those bodies, and therefore the net force due to gravitation is essentially zero. So we can take advantage of those kinds of things. What are the halo orbits?
There are some orbits which are like if you put in that the unstable as such, but like you need very maneuvering is very easy.
Okay.
Yeah.
Excellent. Yeah, I was looking at you because you're from ISRO. So anyway, what we are looking at is something similar to the points over here, but you're looking at it in a more dynamic sense because you're now looking at orbits. So essentially taking advantage of multiple body systems in order to reduce your fuel consumption in traversing a particular thing. So that's where the halo orbits will come very handy. We'll look at more detailed definition of that as well. Okay. Next is in terms of unwanted or wanted perturbations from a existing orbit. So a satellite might be going through a particular orbit, but then suddenly it might face, let's say, a meteor hit or whatever, space debris hit from some other satellites, dead satellites. So things like that. Or you might want to make a small change or refine your current orbit, in which case you do certain firing. So essentially these are the perturbations that are going to occur and how the overall vehicle responds to that, right? Next is we'll try to look at all of these put into the time domain. So a lot of these are coming from an understanding, as I said, of planetary motion, orbital mechanics. We're looking at conic sections, ellipsoidal moments, or in other words, the shape of the orbit is ellipsoidal, or it could be, let's say, parabolic, hyperbolic, etc., depending upon transfer from one orbit to the other or escape, etc. Right? So when you're trying to do all of that, a lot of things can be done without involving the time domain in an explicit sense. Whereas what happens when you try and involve that in an explicit sense is what we'll try to look at in this particular thing, if in case we reach there by the end of the course. Spacecraft attitude dynamics, again, just like I talked about dynamic stability, will not be able to do much justice, but we'll at least try to understand, because we have already some understanding from the fixed wing aircraft's attitude representation. Some of that kind of knowledge will carry over in terms of understanding the attitude of the spacecraft and therefore how it changes with respect to time. Certain things will become simpler because if you're in space, then you don't have the lift and drag forces that you have in coming from aerodynamics over here. But still, there are certain other things which are going to complicate. So we need to have an understanding of that as well. So this is the overall syllabus. Any questions on what we discussed so far? Okay, let's go further. And yeah, some of you are familiar with this, with the YouTube recording. Everybody is able to access it. No issues, right? Yeah. So we have that. And then I introduced one of the TAs, which is Group Captain Nanjapa Hebale last time. The other one is, can you please stand up? Chinababu, Singepogu Chinababu is a PhD student with me working on acoustic black holes, as I mentioned. And so any of you are interested can discuss with him as well. He'll not reveal much, but whatever he can reveal, which he has published, he can probably talk to you about. Then, as I already mentioned, no prerequisites for this course in a formal sense, but any knowledge that you have will definitely come in handy because it will become more like a revision for some of you. The textbooks, I'll not follow it in a true sense of a textbook the way it is followed in many other institutions, but nonetheless, a lot of my own understanding has been influenced by this. So therefore, you will see shades of that coming through as I talk over here. So it's an Introduction to Flight by John D. Anderson. There are many, many editions of that, which is proof of how good the book is, because of which a lot of schools have followed it, and therefore newer editions were required. The other thing, especially from the dynamic stability point of view, maybe a little bit for the static stability point of view also, even though Anderson does a decent job here, certain aspects will be from Etkin and Reid. So that's another book. There are lots of excellent books. Just because I'm listing it here doesn't mean the others you should ignore. if you have the opportunity to lay your hands. For example, for orbital mechanics, there's something by Curtis, which is very good. If you want newer books, because many of these are fairly old, Zipfeel is, I think, a very good book. He works more from a controls point of view, but still the initial portions are things that, because I think there was an edition 24 or even 25, if I remember right. So some of the newer books will try to give examples which are much more current, whereas many of these will be dated, but a lot of these are essentially battered science and math, and therefore not much has changed over the years. So unlike in many other subjects where things change very rapidly, especially in aerospace engineering, this is these basic understandings, not too much has changed. So from the introductory kind of course that we are dealing with, some of the older books are good enough as well. Okay, so to a large extent, I feel the spirit of a person whom I'll name shortly. Some of you, I don't know if might recognize him, but out of many, many others who have influenced me over many different subjects, including this one. So it's a sheer pleasure and rare privilege for me to share that, a little bit of that knowledge with you all. So whatever is good in my course is essentially coming from them. Whatever is the bad is essentially added by me in terms of perturbations that are there. So the little bit of knowledge and wisdom that I've gained from them over many orbits around the sun. Next Wednesday, I'll be completing my 55th orbit. So if this was not already a giveaway. So over these many orbits from so many gurus, back to my academic and spiritual siblings like all of you, trying to share that little bit of knowledge over here. So as I said, one person uniquely stands out as far as this particular course is concerned. So out of the many stalwarts who had taught me in my schools, right from kindergarten to high school to the pre-university, and then as I already mentioned in the previous class, my undergrad, master's and PhD. So this one particular person whose photograph you see over there is and this particular course rather is the way I teach it is dedicated to my greatest of all time teachers. It's late Professor S. Pradeep. The reason I'm feeling a little bit emotional about it is he passed away when he was just 47 years, and he was a wonderful person as a human being, apart from the fact that he was a great teacher. Very rarely you find somebody who's good at the subject is also able to communicate that equally well for people to understand and get hooked onto it. Because a lot of our favorite subjects, if you actually look at it, each of us might have very different favorite subjects, but over school and over college. But typically those are ones which have been taught by great teachers. Not just because you were fascinated by that subject, the initial fascination comes from how well the teacher teaches it, so that then you get fascinated by the subject as well. So that's Professor Pradeep for you, coming from very humble backgrounds in Kerala, from a very poor family, could hardly go to any proper school, and suddenly he saw an advertisement for a school in Ooty, and he packed off and he went by himself. Somehow he got himself registered over there in a residential school over there. Then eventually he saw an advertisement for IIT JEE, and then he went to IIT Kharagpur to do his bachelor's in aerospace engineering over there, and then things are history in terms of what he did after that. Eventually he came to teach here. In 1990 I joined here for my master's. Like you all, the MTech course was then called ME, so master in engineering, but essentially the same thing, but 1.5 years instead of 2. So then so he was young, just 2 years into his teaching, and the kind of passion he had for teaching was kind of infectious, and hopefully a little bit of that has caught on to me as well. Because I feel that teaching is the best way to learn, especially when you're teaching brilliant students like you all. The kind of questions that you ask, the interactions that we have, sometimes lets us think from a very different perspective than we've been looking at the same subject over the years, even though we might be used to it for a while. So this very subject, of course, he taught as two parts. One is flight and space mechanics, like what I'm teaching you here, and the other is atmospheric flight dynamics, in which he covered the dynamic stability parts. And even though this was not my research area, not even related to the project that I was eventually going to do, I still went on and took those the second one, which was an elective at that point in time. So instead of just thinking of them as courses, especially the ones I took with Pradeep were more like joyful roller coaster rides. The way he presented and also tested us, and that brings us to how we will be testing you as well, which we will talk now. Apparently, my students have sent me a slide which I didn't take a look at because it happened while I was traveling over here. So whom we, as I said, unfortunately lost in a timely manner, Professor Pradeep. And in fact, it's an area of research where we've been trying to get people to hire as faculty. Unfortunately, all our search has not resulted in any actual recruitment. So even half a replacement for him is impossible, which is why people like me who don't even work on flight and space mechanics are teaching this course. But the way the course is structured, the passion is more important, and also the undergrad in aerospace will hopefully help in doing reasonable justice, way below Professor Pradeep's, not even asymptotically approaching it, but I'll try to do as best as I can. So coming to, in terms of the way in which the testing will be done, as you know, for all of these core courses, a final exam is mandatory or compulsory, which means that the minimum that I have to allot for that is 40%. And so I will allot only 40% for that. The rest 60% are going to be for fun activities we are going to have in class. And for this purpose, we will have the best of 6. We might have a little more number of problems or projects depending upon the pace at which I cover the syllabus. But then eventually for each of you separately, we'll take the best 6 that you perform in. Just something like the basket rule that some of you might be aware of, that we follow in IISc, right? So these 6, each of them will carry 10 marks each, and 5 will be for group activity, and the remaining 5 will be for individual activity. How we are going to be looking at it, maybe once I give you an example of what is going to be asked, it will become a little clearer. But essentially, it's going to be based on a controversial topic related to flight and space mechanics, which gives room to debates. Okay, so you're most welcome to use not only kind of books that I listed in the previous slide, but any other research papers, etc., but also LLMs, be it Perplexity or ChatGPT or Copilot based on ChatGPT, or any of the Gemini, etc. Feel free to use all of these. But then what is the kind of prompts you're giving it, how you're refining those prompts, and how you're evaluating the responses given by it for its correctness, etc. So those are the things that are very, very critical. So I think we have about 40 approximately number of students. So we will have about 8 groups. Is that right? Is that what you guys decided? Six groups. Okay. Okay. 6 groups. So there's no hard and fast rule how many members can be in each group, but ideally we would think 5 to 10, and those 5 to 10 should have at least one person each who has an inclination towards each one of those 4 areas that we were talking about, namely structures, aerodynamics, propulsion, and the control, navigation, guidance kind of a thing. But if you have somebody who is from an aerospace background who is comfortable with that's fine. We can make exceptions, but overall it would be good to have a balanced team, so that you have at least one of each from each one of these streams, right? because some projects will be a little more heavily inclined towards one of these more than the others, right? So, for example, the initial things that we'll be talking about mostly will be related to aerodynamics, etc. So, it's important for somebody who is a little familiar with aerodynamics to be in each one of these teams, okay? And there are two guys from BTech background, so I want to make sure that those guys, can you please stand up? Oh, you're not here today. Okay, fine. Okay, so they might approach through the video, hopefully, and then I want to ensure that they're not left teamless. So make sure that you have room to include one each in your teams, so that they are also part of the teams. So as I said, it's best six out of the number of projects that we will give you, and each one of them will have a presentation which is more in a constructed in a debate kind of a structure, and then you will argue it out, and the rest of the class will try to put up their own arguments in terms of questions, and you'll have to defend your own whatever you're trying to mention about that. And once you have that, that is going to earn you 5 points for each of those projects in terms of the overall team presentation. So there is a metric which these guys will share later on. And once we have that, based on that, they will be marking that, and I will be cross-verifying that before we upload. So that's just 5 marks. The other 5 marks will be for each one of those. I want each of you, irrespective of which team you are in, to write a 1-page report in terms of what is your individual contribution towards that teamwork, because I know there are lots of free rides that take place in such teamwork. So to minimize that, we will try to see if you can present it in 1 page, and these guys will then check how it correlates with the team presentation that you have done, and whether it has fed into that in some sense, and then eventually evaluate based on that. So that's how these 60 marks are going to be, right? So now, if that is the case, then let's head on to the very first project. I'll give you a more formal probably definition of the problem in a write-up that I will probably do once I get back home today. But right now I'll just try to describe orally what we are trying to do. Maybe once we get into one of these slides, I'll probably connect it with that better. Yeah, this one, yeah. So, as you know, this is the course AE201A, Flight and Space Mechanics. So, upfront, we need to understand what is each one of these terms. Okay, now, this is not your homework. Just it's not going to be as simple as that. So, let me assure you. But even before we get there, I just want to see what we understand by each of these terms, because we take it for granted. We've been using some of these terms almost day in and day out as engineers, and then we think we know everything about it, but there's a lot more that we don't know than what we know. I'm talking of me inclusive as well. So which is why it's important for us to understand what each of these terms stands, so that you understand overall what that course is. In fact, we have already looked at it from a point of view of an informal description, formal description, listing out the topics that are involved, etc. But more than that, in terms of trying to see what you actually mean by each of these terms will actually set you out on the right path. So what do you understand by flight?
Something airborne.
Okay.
It's like using
Okay.
Energy associated with either air or air plus something extra to have a motion.
Okay. Okay. Fair enough.
So motion. I mean, it's a motion through air. Basically, I mean that is how we call it historically. I mean how we use air to fly. I mean, any design which helps us to fly through the air, the trajectory through the air.
Okay. So you all, in that sense, are happy with this bifurcation of talking of flight mechanics and space mechanics separately, because everybody seems to be talking about air. What about motion in space? Is that not flight? So you're pretty much flying in vacuum, rarefied kind of environments.
Trajectory. In short.
Yeah.
This can also be a trajectory, but
Okay.
this implies basically the understanding of aerodynamics to some extent. And in space it's actually how we use, as sir told, how we can use other things, like for example in this case the thrust, and that is how the trajectory in the space. So that really tells about the space trajectory, or in that case.
Okay. Yeah. Good.
In case of flight, we need constant power to sustain a particular altitude or something. But in case of space, once we have reached an orbit, considering no perturbation in the orbit, we will retain in that orbit without even any extra power also.
Okay. Good. So what do you understand by the term space?
There is no aerodynamics.
Yeah. Okay. Yeah. You're saying something? Yeah.
Actually, we can say flight for like anything going through atmosphere, we can call it as flight. Where aerodynamics is very less significant, we can term it as space.
Okay.
Where the altitudes are pretty high and gravity is the major.
Right. Yeah, that's the point of view from which we will be making a distinction in this particular course, the way it is structured in terms of the syllabus. But yeah, you will see people interchangeably using, even in books or papers, flight to refer to orbital motion as well. So don't be surprised by that. Okay. So that's important. But what is most important is the last aspect that we have here, which is what we are going to be focusing on here as engineers, technologists, especially at the master's level. But what do you understand by mechanics?
Motion and forces, driving force.
Okay.
How motion and how force produces motion, and so it's basically.
So it's essentially a correlation between force and motion acting on a body, right? But do you recollect how you ventured into mechanics first of all? What is the first topic that you typically learn, or first course that you typically do when you go to kinematics? Is there anything that you do before kinematics in mechanics? Equilibrium of forces. What do you call that?
Newton's law of motion.
Yeah. Kinematics से पहले क्या होता है? What do you? There's a course. There's a course that you specifically deal with in undergraduate curriculum. I'm sure none of you have forgotten statics. Yeah, statics is considered to be the initial course that you typically do in mechanics. Okay, yes, absolutely true that eventually the goal is to correlate the forces and the motion. But even before we can go into a description of the forces, the other topic that you mentioned, kinematics. What is the difference between kinematics and dynamics?
Force to out, but mechanics as such, kinematics doesn't deal with force. It is just velocity and position.
Excellent. Yeah. So, right. Very good. Yeah. So what you're trying to do is you're trying to build up the complexity level. The eventual goal, of course, is to understand dynamics, which is the correlation between the cause and the effect. The cause being the forces, which we use in a generalized sense because it includes moments as well, and the motion, which includes the positions, the attitudes, the velocities, which are translational, angular velocities, again translational accelerations, angular accelerations, etc. So all these quantities, how the position changes with respect to time, both in terms of in a general sense. Again, position includes attitude also. So essentially how these quantities are going to change. So which means that as you rightly pointed out, kinematics studies the motion without even worrying about the cause, whether there is a cause or not, what is the cause, etc. We don't care. Can we describe the motion? That description of the motion, how various positions, various attitudes change with respect to time, can you get a time history of that? So that's essentially what kinematics is all about. On the other hand, dynamics is then you go into the karma of it. How did it come, right? So the cause for that effect in terms of the motion you have described, how the hell is it happening? There must be some reason for it. And that's where the forces come in, the moments come in, etc. So that's dynamics. Rewind, go back to your very first course, statics. What do you study in statics? Yeah, one of you already mentioned that, equilibrium, right? So essentially you're trying to look at these two separately. So statics is essentially trying to look at those causes alone, and this is trying to look at only the effects alone, and then you're trying to marry these two, and then you're trying to look at what you're looking at is the dynamics, right? So now in statics, therefore, you have equilibrium, as you rightly mentioned, which is essentially trying to see under the existence of certain external forces and maybe certain internal forces also, which could be body forces, for example. Under these distributions, the body is at rest, right? So which means that these are all under equilibrium, and so then you try to determine certain known quantities, unknown quantities in terms of the known quantities by using these equilibrium equations, force equilibrium, moment equilibrium, etc. Okay, and you could then make it a little more complex with multi-body systems, etc. But then once you get into kinematics, you understood how the positions and attitudes change with respect to time, then you can take time derivatives of that, because they depend only on time. Then it's an ordinary derivative that you're dealing with, and ordinary differential equations. And if you have ordinary differential equations that you have to solve, you get a general solution. But if you want an actual particular solution, you have to go for initial conditions. So that's something that comes into the picture as well. Then once you have all that in place, then you start looking at the forces. So some of the forces might be known, some forces might not be known, and there might be certain scientific principles which are governing some of these. For example, we wrote GMM by R squared as the gravitational force. So something like that, what is the theory behind that? So that may not be directly related to the motion, but what is the source of that? In fact, gravity is the least understood. If we say that that is an explanation of what it is, then we are trying to oversimplify it, but let that remain. At least for us engineers and technologists, it works, and maybe not for scientists and for human beings as such. Okay, coming to the putting together of all of these. In the last class, I was talking to you about the similarities between ground vehicles and the aerospace vehicles, or flying vehicles or flight vehicles. What are we thinking of in terms of the differences? The primary difference, where you say this is not a ground vehicle but a flight vehicle.
Wheels present on wheels.
Yeah?
Presence of wheels.
Presence of wheels, yeah. So eventually some of these are going to be landing on ground or taking off from ground, which means you will have landing gears there as, yeah, for the major portion of the mission that you're talking about, right? Yeah, you don't need wheels to do that, right? Yeah, so what do you need?
Propulsion system, different type of.
Okay, but doesn't the ground vehicle have a propulsion system? You may not be calling it seriously by that name, but essentially what is propelling? Propelling is something which is taking you from point A to point B, right? It's essentially trying to push you in that direction or pull you in that direction, right? So that force, how it is generated is a different story, but essentially you need that in the ground vehicle as well as here. So that's not so much of a distinction. Of course, how you generate it is a huge difference, because typically most of the ground vehicles are IC engines, and now these days electric vehicles as well. But then for flight, you mostly use gas turbine based jet engines, right? Though you still have IC engines also over there. So there is a kind of an overlap, but there's something which is distinct. Aerodynamic? Very good, yeah. So aerodynamic design is much more critical over here, because exactly. So all of your performance parameters and also the fuel consumption, everything is going to be directly related to that. And if you want those within the desired range, then you obviously have to do an aerodynamic design. but the kind of aerodynamic design which goes into a racing car or for any of these sporting entities, even a bike, for example, for cycling in the Olympics, or even the design of, let's say, a golf club or a tennis racket, etc. Many of these, of course, they use, a lot of these use carbon composites as well. And in terms of the shaping also, a lot of thought goes into the aerodynamic design over there. So that alone is not sufficient. So wherever motion is involved, you need to see where is the resistance to that motion coming from. You're absolutely right, there are wheels and therefore friction is the more dominating thing. But in fact, for racing cars, you need more friction, which is why you have spoilers and you try to reduce the lift and try to make it heavier, therefore it has a good grip on the ground, right? So you typically use spoilers. Of course, use spoilers in aircraft as well. But what is so can you take it a little further in terms of aerodynamic design? What are we actually looking at?
So for ground vehicle, downforce is more important, but for flights, we need lift.
Exactly. So that's the key word there, lift. Okay, so that is what is going to be dictating these, especially in the atmospheric flight that you're going to have. You want to utilize the medium in which you're flying. Okay, you of course don't have the luxury of that in vacuum, but at least when you have an atmosphere, you may not even have that luxury in lean atmospheres like those of Mars, but at least where you can utilize it, like in Venus or the Earth, you want to utilize that to generate the lift force. Because all said and done, remember we talked about a 2D motion in the previous class for ground vehicles. Okay, it's not on a flat surface, it is a curved surface, but at the same time, essentially there are only two coordinates which are required from a translational point of view in terms of marking your CG. So of course, the shock absorbers but that motion is very small, the vertical motion in ground vehicle compared to the distances traversed in the X and the Y directions. So that Z direction motion is going to come into picture over here. Again, when you go to space and you talk about orbital mechanics, remember I talked about two topics there, 2D orbits and 3D orbits. You might have simplified cases over there when you're again going back to 2D motion over there, in which case just two coordinates are sufficient for you, either associated with the rectilinear kind of motion or the circular or elliptical motion. Both can be essentially given either in terms of an XY coordinate or let's say R theta coordinate or whatever. So, but essentially only two, right? But in most general cases with flight and space mechanics, you're dealing with a three-dimensional motion. And when you have a three-dimensional motion, till kinematics, it is okay to just talk about the motions and the attitudes. But then when you're going into dynamics, you need the cos. So therefore, the cos is the force, and that force is the unique force of lift, which is not talked about as much in designing of ground vehicles, etc. So that lift is what is going to be critical. So glad you answered that, because the first homework is going to be about lift, right? So lift is what distinguishes ground vehicles from flying vehicles. Now you need ample amount of lift depending upon the particular design that is involved. Most importantly, what is the weight of the aircraft that is involved. Now, how is that lift generated? Okay, so we are going slowly backwards, right? We know what kind of motion we want, what kind of motion is required of this particular aircraft. So it needs to perform a particular mission, which means it needs to, first of all, taxi, take off, climb to a certain altitude, then it needs to cruise, and when it's ready, it needs to engage with the enemy because it's a military aircraft. So the kind of maneuvers that it needs to perform, pull-ups, etc. We'll look at some of those also in terms of the equations which are governing that. Then once it is done with that, or if it's a reconnaissance mission, it's essentially trying to get an idea of the enemy territory, and then eventually it comes back, and then it has to descend, and then it has to land and taxi back to the hangar, right? Or for maintenance or whatever. So when you're doing this, each one of those phases of flight will have certain requirements, and each one of them will have a certain lift that is needed to be generated. Okay, sometimes even negative lift depending upon the maneuver which is involved. Okay, so now when you are trying to accomplish these maneuvers and get that kind of lift, what is the agency or entity by which you're generating that lift? Wings. So that is the predominant contribution to the lift that is going to be there, right? Now, what is it about the sizing and shape of the wing which makes it efficient enough to generate lift? Unlike, let's say, the fuselage, or these surfaces are also, in a sense, aerodynamic. They can generate forces, but because their sizes are small, it is not as much as what the wing generates, right, for typical motion. So what is the shape aspect of the wing which makes it suitable for lift generation? Slenderness. Very good. Yeah. So how does the slenderness help in the lift generation?
Larger platform area, larger area in general, more air can be diverted and the pressure difference can be obtained.
Okay. Yeah. So essentially you're talking about in terms of the dynamic pressure times the reference area that is involved. So more the lift required, which is the case for heavier aircraft. So when you have a heavier aircraft, you need more lift to be generated, which means one way of doing it is by having a larger platform area, right? Now that's fine. Now coming back in terms of the shape aspect, one is the platform area, which you see in this particular case is triangular, which we call as a delta wing, right? And anybody why use a triangular kind of a shape over here, which you don't see in, for example, the Beluga that I brought last time, or any of the commercial aircraft? What is the
The Mach number range, it plays based
Yeah.
on that it is big.
Okay, can you elaborate a little more on that?
You can travel at higher speeds.
Higher speed, this is rated.
Shape.
Okay, okay. Yeah, why? Exactly. So essentially, one thing is, as he pointed out, we want to maximize the lift. The other is we want to minimize the drag, okay, which is opposite to the thrust that is, because more drag that there is, the more thrust you need to generate, which means the engine has to be more powerful and or the fuel consumption has to be much larger, which means that not only are you trying to generate an ample amount of lift, which is going to be predominantly dictated by the weight, gross maximum takeoff weight of the aircraft, but also you want to minimize the drag. And when you want to minimize the drag, again, shaping becomes important. And in fact, these two can be clubbed together in a single parameter, what we call as the L by D, the lift to drag ratio. Okay, and later on we will see this is equivalent to what is known as a CL by CD, which is the lift coefficient of the aircraft, which we will define shortly, divided by the drag coefficient CD. So CL by CD, we want it to be a maximum. Now we are trying to understand it in a little more deeper sense. We already said one aspect of the shape is essentially the platform. This we call as the platform because you're seeing it from the, remember we introduced the X coordinate along this, Y coordinate along this, the body axis. That compared to that, you're essentially looking at the XY plane. That is essentially your platform that you're looking at. Okay, one is the sizing in terms of the area. The other is, as you pointed out, the shape. In this case, you have something called the wave drag, okay, which comes in when the Mach number gets into supersonic and or hypersonic regimes. Your wave drag becomes one of the critical or large contributors to the drag. We will not look into it so much from this particular course. There's a course going on in parallel in terms of an elective in terms of gas dynamics, for example, where you'll be dealing with a lot of the shock waves and the drag associated with that, etc. But right now, one thing is for sure, irrespective of whether it is supersonic like this or the transonic kind of aircraft, which are predominant today in terms of commercially flying transport aircraft, in both of these situations, apart from the wave drag, there are other drags, okay, parasite drag, induced drag, skin friction drag. All these drags are also going to be dictated by certain other aspects of the shape. It's not only the planform shape, but also certain other aspects. What else can you talk about in terms of? Exactly. So that's the most critical thing in terms of what is the cross section. So if I cut this wing parallel to the xz plane, where z is along the vertical direction and x is along the nose. So if I cut this, then I get a particular shape, which is a very, very special shape, airfoil shape. There are many, many standard airfoils, what we say as the NACA series, and then depending upon specific regimes that they're going to be flying in, like low Reynolds number, etc., you have many other kinds of airfoil cross sections which are more suitable for them as well. But essentially, you're coming back, when you're talking of an airfoil, you're coming back to one of the other things you mentioned, slender. Okay, the slender term that you mentioned is essentially related to that. So essentially, you're looking at, instead of a bluff body, like for example a cylinder, you're trying to come up with a slender body, which is essentially one extreme of which is the flat plate. Okay, so if you have just a flat plate, you see that when it is kept in the direction of the flow, you may not see any lift generated, but once you start giving it a small angle of attack, you essentially see a upward force. Very familiar for children putting their hands out of the car window and experiencing that upward force, right? So that's essentially the lift that is being generated. Now, it's been 123 years since the Wright brothers flew, and much before that, much after that, and even until date, this topic of how exactly that lift is generated is still a controversy. We better not, as aerospace engineers, discuss this with somebody who's not into it. They might be scared of flying, right? So we've designed amazing aircraft, a lot of amazing performances, etc. There are many theories, not that there's lack of theory, but there are just too many theories, and each proponent of the theory and their school of thought, which comes after them, has been saying that theirs is the answer to that question. But there are heated debates in terms of how exactly it gets produced. So some examples, can you think of why should an airfoil generate lift? Very good, very good. Yeah, so that is one of the major arguments. What is happening is that you need lift which is defined as not necessarily perpendicular to the wing, but perpendicular to the velocity vector. So if the relative velocity between the wind and the vehicle is in this direction, as I'm showing with my left hand, then what you're saying is that the force which is perpendicular to that is the lift, and the force which is along that is the drag, by definition, right? So now if you want to generate that particular lift, as he rightly pointed out, you need a certain pressure distribution to be in a particular favorable way. What is that favorable way? Essentially what it means is that if you want a force in this direction, you want to have a lower pressure on the top and a higher pressure at the bottom. A lot of people use the word or adjective suction pressure to deal with it. There's no such thing as suction pressure. Pressure means it's always compressive by definition. If you look at it as a stress, it's always negative, okay? The pressure can never be tensile in nature, okay? Just that relative orders of magnitude we are talking about. The pressure on the bottom is much, much larger compared to the pressure distribution on the top, and therefore the net effect is that it gets a push up, it gets a lift, right? So that is one way of describing it. Yes, using that approach, we can calculate the lift also, not just qualitatively describe, but actually calculate it. But how accurately we can get that pressure distribution, either experimentally and or theoretically and computationally, is again not something that is everybody agrees upon, okay? And many a times you find that the amount of force that is generated, it's actually a blessing in disguise, higher than what this can actually calculate for you. So what exactly can be happening other than this pressure distribution alone, which again, what equation will you use to get this pressure difference, for example? Navier-Stokes, yes, that's the ultimate you use for everything. But can you use something simpler also to just to get a ballpark value of Bernoulli's equation, right? So P plus half rho V squared plus rho GH is a constant, right? Now, a lot of people forget when they're using certain equations, its applicability. What kind of assumptions have you made to derive those equations? Even if you have not derived, whoever has derived, what are the assumptions that they have taken in order to, and are those assumptions valid here or not? Okay, because now you're talking of two streamlines, one streamline going on the top, another streamline going on the bottom, and then you're applying the same thing, and then you're saying that P plus half rho V squared, well, the velocities are much lower here, therefore pressure should be higher. Velocities are much larger on the top, the speeds, and therefore the pressure should be lower, and therefore there's a net differential pressure and it moves up. Well, the end result is fine, but the logic in the argument, there is a lot of loopholes, lacuna that are involved. Okay, so all of that will be part of your presentation, so I'm not going to some of those details. We'll discuss that after your presentations in terms of consolidating everything, but that is one thing. So Bernoulli's equation, pressure, anything else? Explanations for
Momentum change.
momentum change. Okay.
Which the airfoil brings into the orientation. We know that aerodynamic forces are a result of any orientation in the flow field.
Very good.
Essentially,
Very good.
we're using that to introduce a momentum change and thereby getting a resultant, Newton's third law.
Excellent, excellent. Yeah. So that is one, again, very, very common explanation. In fact, what he said includes two different aspects. One is, as he concluded, the Newton's third law, okay, which is every action has an equal and opposite reaction. And this is something very beautiful because when you're looking at micro structures at very small length scales, the only law which doesn't break down, at least so far we have found no breakdowns, is this Newton's third law, which always works, irrespective of what kind of physics you're talking about, be it mechanics like what we are dealing with over here, whether you're talking of electricity, dynamics, magnetism, whether you're talking of optics, whatever, all these different branches of physics, you see that this always happens at the micro level. Whether it happens at the macro level or not, we don't know, because most of the macro quantities are statistically averaged out micro quantities. That's what we deal with. Whether we're talking of all these quantities that we discussed earlier, remember, pressure, density, temperature, etc. They are all statistical definitions of what is happening at the particulate level, at the molecular level and or atomic levels that are involved in different kinds of entities that are involved, right? So now, you're talking about Newton's third law. Yes, it is very much valid. So what we are talking of, put in a very simplistic sense, you explained it beautifully, but to put it in a very simplistic sense is when there are two entities, whatever force one exerts on the other will exert the other on the first one in the equal and opposite way, right? So in other words, as the aircraft flies, it is having a certain force on the medium, that is the air that it is flying through, and that is essentially downward in nature, and therefore the air pushes it up, which is essentially an equal and opposite reaction, and therefore there is a force. Again, absolutely nothing wrong with this argument either, but you can actually go try to calculate this particular result, and you will see that once again, blessing in disguise, lift is more than what this can estimate. So obviously there's something more of grace that is happening in terms of how exactly it happens, right? But as scientists, we don't just leave grace without a mathematical model either. We want to mathematically model that grace as well. So what is that grace coming due to? So now you have already ruled out or actually included partially the Bernoulli's equation, pressure difference, the Newton's third law. One more aspect which you mentioned in terms of the curved surfaces, the momentum transfer, which is more commonly known as Coanda effect. Coanda was a Romanian scientist after whom this is particularly named. And essentially what happens is whenever there is a surface that is there and any fluid flows about it, including air, then there is going to be a certain circulation that is involved, because of which there is going to be a lift generated. So one more way of doing it, again you try to calculate it, again it estimates reasonably good, but still there is a slight shortfall that is over there. So then some people then say that we've all been too theoretical, hard-headed. Mostly it's mathematicians and scientists who've been doing it instead of engineers who don't know how to fly. None of them have designed an aircraft. So there must be something really seriously wrong with this whole approach of how actually it takes place. One is go back and check your assumptions. Most of the people are dealing with incompressible flow, inviscid flow, ideal fluid, the P is equal to rho RT kind of ideal gas equation is valid. Then you people are talking about irrotational flow. So you look at the many number of assumptions that are made in order to derive some of these equations. Yes, of course, you have the Navier-Stokes where a lot of these have been left out in terms of unsteady flows also, including turbulence, etc. But it's $1 million for somebody who even proves that there is a general solution for the Navier-Stokes, leave alone actually solve it. Of course, there are DNS and various other workarounds for that, for various simpler cases, but the most general situation, you still have $1 million price on that. Now, therefore, this particular exercise for you is going to be for you to divide yourselves into teams, a minimum of 5 to 10 people. And what you're going to, each one of them is going to choose, discuss amongst yourself and choose one of these things that we talked about. Let's say one chooses the Bernoulli equation. Let's say it's because of Bernoulli equation. The other chooses Newton's third law. Other chooses Coanda effect. Other chooses viscous effects. If you're considering instead of inviscid fluid, viscous fluid, there is a lift which is generated because of that. In terms of what kind of happens as the flow takes place in terms of the separation or not, and if the separation is taking place, what is the pressure difference that is happening because of that. Then there are people who deal with vorticity. Okay, now you already agreed that there is a higher pressure at the bottom and a lower pressure on the top. Okay, now this is beautiful for explaining 2D versions. That is just the airfoil, where you think of the chord as very small compared to the length of the aircraft. In other words, infinite aspect ratio. So wind tunnel tests of these can also be done in an approximate sense, asymptotically approaching, and then you have 2D results. Then you come to 3D. There are other aspects, how the aircraft is generating the lift or how the lift is getting modified because of this. One is because there is a high pressure here and low pressure here. At the tip, the air has to go around, right? So in other words, the air goes around like this, which is essentially creating a vortex, right? And that vortex is shed and it goes back, right? Now that also has some kind of an effect in terms of the lift generation. Because remember, at the end of the day, it's the difference in the integrated stresses which are acting on the bottom and the top, right? So which is what is going to give you both the lift and the drag, okay? So now, when you're trying to do that, there are two kinds of stresses. One is the normal stress, which we have all been talking about, which is the pressure. But then there is also a shear stress which is acting, which is essentially a viscous forces. And that viscous forces are also going to contribute. Of course, they contribute much more to the drag than they do to the lift, but still there is an effect because of them. And then whether you have a so-called laminar boundary layer or a turbulent boundary layer, where it's going to separate, if at all it's going to separate, then how you utilize other aerodynamic surfaces like slats, for example, which are leading edge devices which move out, and then air flows from the higher pressure to the low pressure, and therefore tries to energize the flow on the top, and therefore tries to push back the point of separation, and therefore increase the amount for which you have an attached flow, right? So there are many things that are complications that are involved, but we will stick to just the base wing without all these lifting devices, the flaps or ailerons, whatever you have, and then the slats, etc., forget the spoilers, etc. You can probably use them to explain some concept or whatever, but that's not the main thing that we are looking at. We're just looking at the 3D wing. You can start from the 2D airfoil and go to the 3D wing and then reason out based on all these effects that we talked about. And don't limit to these. I just gave you examples of these based on your own inputs, be it Bernoulli's equation, Newton's third law, Coanda effect, viscous effects, okay, and these vortices that are generated, the tip vortices, okay. There could be many, many more as well. There are also lots of schools of thought which say that these are equivalent ways of describing the same thing. Not necessarily. There could be overlaps. Okay. In other words, you don't just get each one of these 5 and add them up. You don't get so much blessing in disguise. Okay. So you'll end up with a much higher lift estimation than what actually is. It's just that certain things captured by this are also captured by this, but not all of it. There is something additional which is captured by it, and that question is, how do you put them all together without repeating them, right? So that is the way in which we eventually want to go. But purely from the point of view of this exercise that you're going to do in class, I want each team to stick to one aspect, not say, okay, this also, that also, that also. Okay, that we know eventually. That is the current state of understanding of where we are. But historically, there have been huge arguments, even to some extent. Of course, you have the chicken and egg story, but people say that the wars were also fought on these, both the world wars that were there, the British side in particular, and the German side, the kind of thought process that they had. Okay, Lord Rayleigh and a group from Cambridge in the UK, and then Prandtl from the technical institutions of Germany, Munich, etc. And then we are talking about, in terms of the understanding, basic understanding, how the differences were kind of fought one with the other. And then, of course, the American school, where they said, to hell with all of your theories, we are just going to make and fly, trial and error, like the Wright brothers did. Of course, they did a lot of experiments, they studied a lot of literature, they saw a lot of that literature was rubbish, nothing works. And then they decided to let us throw that out and we will just trial and error. We are bicycle manufacturers. We'll use some of our bicycle parts and try to put things together. But all of this eventually came after a lot of studies that they had done. But as far as we know, they didn't have any college degrees or whatever. And that comes against what the Cambridge people think of in terms of the hierarchy, in terms of people, understanding and explanations, and therefore there was always this argument. Similarly, the Germans took a middle path, neither going to the extreme of the Americans and saying only what actually practically works, or to the British way of looking at it, where only theory, everything that has to be, first of all, validated by rigorous theory, math and physics, only then we can take it to the next level. So now that's where Prandtl and his Kutta and of course Zukowski, though he did it independently, all of that knowledge essentially comes. And then some of the studies that you're going to do might go on these historical lines as well, but I would say keep it to the minimum. We don't want to be talking too much about that. We want to be basically understanding the science that is involved, the equations that are involved, and how you can kind of explain the various phenomena that are taking place and how each one of those contributes towards the lift. Okay, is this clear? Yeah. So that's as far as this is concerned. I will, of course, as I said, I just write up briefly on whatever I described, but I think I probably did a better job orally speaking than what I would write. Okay, and maybe you guys want to add something to what I said?
Definitely, what you said is fine. You have already mentioned everything they wanted to.
Okay.
You left few things for them. Let them guess.
Sure. Okay, right. So that's so as I said, so there is going to be a team presentation, then the individual contributions 1-page report for each one of these exercises. The first exercise is what I have now described in terms of understanding where this thing which majorly distinguishes flight from the ground motions, surface motions that we have, which is essentially the lift, and how that lift is generated. What are the causative factors, both from a qualitative point of view and the quantitative point of view in terms of the equations which are governing all of that, right? So that's what we will do. Then let's go. Yeah. So we just described this. So it's 1903, but they flew in 1902, they flew in 1901, they flew in 1900 also. Just that those crashed very quickly, and it was not a powered flight. In some cases, it was glider flights, because they were also to a large extent taken forward by Otto Lienthal's work. Otto Lienthal did a lot of work on gliders, and he was very successful. And many of his hand gliders flew for fairly large distances, just that the last gliding flight he had, maybe the 16th or 17th, I may not be perfect about the number, it crashed and killed him. So what people started looking at is only that, and said he's a failure. All of his designs which went before that don't get the recognition that they deserve. But these guys were smart. They studied all of Otto Lienthal's work. They studied George Cayley's work, which in terms of the understanding of lift, etc. So all of that, and then they found each of them having a certain lack, especially when they built their own wind tunnel and they tried to test it, because they are essentially from Dayton, Ohio, which is a state where you do not have to, or a town where you do not have much of winds. So therefore they tried to search right to all these weather related government entities, trying to find out which are the locations where there is a lot of wind activity, which seasons they are in, etc. And they try to understand that, and then they earmarked Kitty Hawk for this particular flight. And eventually the one which was successful, or in fact a series of flights on that particular day which were successful, were this. But of course the endurance involved, or the range involved, was much smaller. But then they took it much forward until the elder brother Wilbur passed away in 1912, when Orville just gave up after that as well, just retired to his mansion. But from the late 1890s all the way up to 1912, they did a lot of work, not only in the US. They tried to sell their ideas and their actual airplanes even in Europe, because that was just building up to the World War I, and therefore there was potential large market. So they were not only great scientists, or in a practical sense technicians, but also good entrepreneurs, okay, and which is also becoming more and more important for you engineers in terms of being job seekers to become job providers, and the huge amount of potential with a lot of startups. Of course, there's a huge risk involved, but there have been those who have been successful, have been really successful, and there's a lot to be gained from that as well. So it just happens to be 2026 happens to be exactly 123 years, which is 123 years, and we have had many different kinds of military aircraft as well as civilian aircraft which have flown, and some which have outlasted the typical years that they were originally designed for, in terms of the individual aircraft as well as the design and manufacturing processes. Some have been curtailed, shortened than what they were expected. Cases in point are the Concorde, for example, and also A380, for example, very large aircraft. About 80 meters in span and or length. So some of those have, you can't say actual failures, because about 250 of the A380s were sold. The Concorde also, as long as it lasted, it flew quite a bit. And the only reason it was grounded was one accident, which was kind of fatal, right? So flying machines, aircraft, but not all of them are really good or successful within quotes, which essentially come up with leftovers. In fact, people have made careers out of compiling those as well. You see this particular book by Bill Yen talks of the world's worst aircraft, okay? And so many of these that you see, because it's an older edition, you see are older aircraft, but there are many newer versions also which have failed, which are not taken off. Because you're talking about, one is when we say that good or successful aircraft, what essentially you're talking about is a word which is flight worthy. Okay, first of all, the certifying agencies should determine that it is flight worthy and give you a flight worthiness certificate, and then even after that, it's not for sure. It has to be a commercial success in terms of selling it. Even a military aircraft, you have to sell it to the air forces and the navies around the world, right? So, and in the case of the commercial flights, to the airlines that are involved. So the commercial success again is not guaranteed, and it is controlled by so many other factors. The timing also matters. When you started doesn't matter. When you actually come to the market is what matters, and what is the market situation at that point of time, what are the geopolitics going on at that particular point of time, etc. So all those things come into picture. But all said and done, there's a lot to learn from this particular first flight. One, of course, it's a biplane. In other words, it involves two wings, and therefore you talked about the wing area need to be large enough to generate the lift, which is commensurate with the weight that is involved, a slight fraction above that, obviously, to take care of various other aspects which we'll discuss when we go to the Venn diagram. But essentially, you're splitting that. That is one split. The other split that we already discussed in passing in the last class is essentially the propulsion and the aerodynamics. So the wing generates only the lift, not the thrust. The thrust is generated by the engine that they designed. Okay. Now, most of the people around the world who are trying to fly, and there were many of them at that point in various countries, especially North America and European countries. And when they were trying to do that, they were only thinking of these two aspects, that is aerodynamics and propulsion. A lot of people didn't think as much about controls, whereas these guys were smart enough. They designed the controls for that. They were observing birds as well in terms of how they move their tails, etc. And therefore, they decided they should have appropriate controls, because stability was the biggest problem. Okay, not aerodynamics or propulsion. Yes, as long as you did certain things in an appropriate way from an understanding of what has happened before, you were able to reasonably handle that in many cases, many of the designs that came up at that point in time. But controls was still a very nascent subject, especially controls in flight. Okay, of course, controls on ground in terms of how you control a vehicle on ground, it was very well understood. But now that you have 6 degrees of freedom instead of 3 degrees of freedom that you have on the ground, because so it's just X, Y, and the rotations that you have, and little bit of the other things for banking and other things, but they're negligible compared to the other motions that are involved. So having controls for this, and at the same time stability to a reasonable extent. So because these two are counterproductive, as I mentioned last time. If you have a very stable aircraft, difficult to control or maneuver, and vice versa. So therefore, you should know for a given design, what is the level of controllability, what's the level of stability that you have to build in all the three different aspects, be it roll or yaw or the pitch, and some of these are coupled as we discussed, and therefore you need to address those as well. Okay. So now let's look at certain typical aircraft. One of the most successful aircraft, apart from the A320 series, has been the Boeing 737. A large number of aircraft have been sold to airlines around the world. So you get a basic understanding of how the aircraft looks just by looking at this particular thing. There are, of course, subtle variations as you go from one aircraft to the other. For example, you see that the wing is attached to the lower part of the fuselage over here. Sometimes it could be attached at the mid or on the top. You get what are known as low wing, mid wing, the high wing kind of configurations. Here you see a certain taper that is there, which is very common. You start with something which is having a large cord where it is connecting to the wing, to the fuselage, which is essentially a wing box over there. And then it essentially tapers down. And again, many different reasons for that. One is the stresses are very large here, so you need a larger cross section to be able to handle that. The other, of course, is in terms of the aerodynamics. Just now we were discussing tip vortices. So anyway, that is not going to generate, this cross section over here is not going to generate as much lift as the inboard cross sections. In fact, the ideal way in which the lift is distributed along the span is elliptic in nature, an elliptic lift distribution. How actual lift distribution differs from that is also something that is typically used in the lift calculations that you'll observe when you go through the literature. But essentially, since the lift is very small, their drag is also very small, you don't need such a large cross section over there. And again, in terms of the winglets that are there, how you design that, how that affects the vortex, trailing edge vortex flow. So all that is there. Then you come to the fuselage shaping, and then in terms of the conventional design, which is what we're talking about over here, whereas some aircraft could have that stabilizer up front, what we call as the canard. But for most of this class, we'll be talking about a rear tail that is going to be involved over here, the horizontal tail and then the vertical tail. And typically, the books like Jane's All the World's Aircraft, for example, which is available in our library, will show you the engineering drawings of that. You see the side view over here, you see the top view over here, and also the front view. And then if you cut it somewhere in between, you see a sectional view that you see here, which is why you're seeing the seats inside the fuselage over there, right? So now you have a situation like that. Then, of course, you have the engines. Again, for commercial aircraft, you'll see more than one engine for a safety point of view in terms of the reliability that is required. Whereas a lot of military aircraft, you will see just a single engine. Again, there could be differences depending upon the size of the aircraft and the kind of missions that it is planned for, right? So now, in terms of the nomenclature, all of you are familiar that this middle portion is called the fuselage. Now, slowly, the blended wing body design is coming up, where you lose the idea of where is the wing and where is the fuselage. Becomes one single entity that is being designed. There's a lot of work going on in that as of today. But this, again, we're talking of conventional designs. So you have a fuselage separate from the wings, and where the engines are mounted, again, there could be difference. Some aircraft could have engines which are mounted on the fuselage and or the wings as well. In terms of the fuel tanks, where they are located, typically in the wings, there could be some fuel tanks in the fuselage also. Again, depends on the design and what all it carries, etc. And then the control surfaces that we already talked about. The inboard, what we have is the flaps to increase the lift, especially in takeoff and landing. And outboard, where you have the ailerons, which are going to deflect in a differential manner in order for it to roll, right? Then in the vertical tail, you have a control surface which we call as the rudder, which is controlled by the pilot's rudder pedals, and that's essentially to yaw. That yawing motion is over there, right? Then you have in the horizontal tail, you have a trailing edge surface again there, which is the elevator. And when you deflect the elevator down, you get a force upwards, which is making it pitch nose down, right? So the other way, of course, if you deflect it upwards, you could pitch it nose up. So now these are the overall major things. In addition, we briefly mentioned slats that you can see over here, that these are the slats at the leading edge high lift devices, and these are typically moved out and downwards so that there is a gap in between them. The high pressure air flows through that, comes to this particular thing, and then the flow separation is essentially delayed on the upper surface of the wings. So, and then, of course, there's a lot of thought which goes into even what might be thought normally as not such critical engineering things, like the window design, for example, in the door design, etc. There's a lot of engineering and science which goes into that as well. And some of these, unfortunately, were learnt because of certain accidents which happened. For example, when you have rectangular wings, you could have stress concentrations at the corners, which is why you see now rounded off corners. Then you also have laminated glasses, which are chemically treated. And then on the outboard and the inboard, you don't have glass but acrylic, which is much stronger and stiffer. And then some of these acrylics will have holes because the internal pressurization is there, and you don't want to create a huge gradient, and then in terms of the temperature and pressure, some kind of equalization is done through the holes in this. Similarly, in terms of the door design, again, it needs to open in an emergency as at the same time for regular operations as well, and again taking care of the internal pressurization, etc. So a lot of things which go into that. Then in the front portion, there's a possibility of bird hits, especially closer to takeoff and or landing or climb or descent. And then depending upon the kind of airports and what kind of environment you have around the airports, for example, if a lot of meat shops, etc., the possibility of birds is much more, and that can have an impact in terms of the radome design over here, into which the weather antenna is typically located. Then you have measuring devices that you see over here, which are pitot probes. Okay, you have a static probe and you have a dynamic probe to measure the stagnation pressure and the static pressure, and then get the difference between them to get to the dynamic pressure. So all these various aspects are there. Then in terms of the nuances of the landing gear that are involved, the nose landing gear and the rear landing gear that you have over here, what materials are used to build each one of them. Even though you might have a large usage of composites in the rest of the aircraft, typically some of these are still made out of steel, okay, even though it has a very, very high density and low specific strength, low specific stiffness, because certain features of the steel are still more attractive towards the landing gear over there. Then in terms of the wing, as we know, this is a plane of symmetry, so both wings look identical, but we still need to distinguish between them, which is why we call the right wing as the starboard and the left wing as the port. Okay, these don't seem very intuitive, or I don't know the etymology of that, but the way I memorize this is, this has 2 R's, so it should be on the right side. This has only 1 R, so it should be on the left side. So that's how I used to remember as a bachelor, and I continue to do that probably. Now, coming to the horizontal stabilizers, we already discussed, and the vertical stabilizer is on which the rudder is there, that also we have discussed. So I think with this, we'll probably end today's class. We'll continue. I'll just have a brief write-up on the assignment that I described, and all of these homeworks will be due exactly 1 week from which it is given to you. So which means today is Monday. So again, Monday is when we'll start the class with your presentations, a consolidation of that, and then continue the rest of the class. Wednesday, there's no class, as I already mentioned. Thank you.